Good evening, everybody. Welcome to Mexborough and Swinton Astronomical Society. Still going along every week for the past 2 years, so we must be doing something right. So I will introduce our speaker. Sunday name Victoria Fawcett, but evening name Vicky, and welcome to Vicky. Vicky's a final year PhD student at Durham University researching quasars. She did a master's project at the University of Warwick, where she researched the X-ray irradiation of exoplanets. And her research now focuses on dust-reddened quasars and whether they could represent an important phase in the evolution of galaxies. So tonight's talk will be monster black holes, active galaxies, and red quasars. So please all put your hands together and welcome Victoria or Vicky Fawcett. Thank you.
Thank you very much for that lovely introduction. And yeah, it's great to be here talking, virtually. So yeah, I'm Vicky Fawcett. I'm a final year PhD student at Durham, and my supervisor is Professor David Alexander. So just, yeah, a little bit about me, but we've already had a nice introduction. So I did maths and physics at the University of Warwick, where I graduated in 2018. And I also did a master's project at Warwick in exoplanets. So feel free to ask me some stuff about exoplanets, but I basically decided during the master's that I really enjoyed researching astronomy, but exoplanets were, just a little bit boring, and I wanted to go for something a little bit more exciting and exotic. So I decided to go for a PhD at Durham University, where I'm now part of the Centre for Extragalactic Astronomy, researching quasars. And also just to note, I've as of this week, I have got a job offer at the University of Newcastle to be a postdoc. So I'm going to continue being in astronomy for at least the next 4 years, which is, yeah, I'm very happy about. So before I go into what quasars and red quasars are, I'm just going to start kind of from basics. So hopefully everyone knows kind of the concept of a black hole. So black holes are incredibly dense objects, and they have so much gravity that not even light can escape, which is why they're called black holes. And they're formed from the collapse of massive stars. So you have a star that's about 25 times the mass of our sun. When it gets to the end of its life and it runs out of fuel, it will collapse down and into a point and form a black hole. So there's two kind of important parameters for black holes. There's the event horizon, and this is essentially the classical size of a black hole. Once you're beyond the event horizon, it's the point of no return. You can't escape, even if you're traveling at the speed of light. There's also an accretion disk. So this is a very bright disk of matter that is orbiting the black hole. So like the planets go around the sun, because the sun has gravity, you have a lot of material that orbits the black hole. But the black hole has so much gravity that the material in this accretion disk rub together, and that friction causes heat, which causes light. So when we talk about observing black holes, we're really observing this accretion disk of matter. So how large are black holes? This is the only bit of thinking you'll have to do in this talk. So I have the whole Earth. How small would I have to collapse the Earth in order to form a black hole? As in, how dense would you have to collapse something down in order for it to have enough gravity to be a black hole? So the answer for this is the size of a penny. Although a child did point out to me that a penny is technically 2D, so I should really replace this with a marble. So you take all the mass of the Earth and you crush it down to the size of a marble, and at that point you would form a black hole. So this is just kind of demonstrating how incredibly dense objects these things are. So how do we know that black holes exist when we can't actually see them? So there's a few ways we can indirectly observe black holes. The first way is through binary black hole systems. So the two kind of main flavors of binary black hole systems are On the left, where you have a black hole orbiting around a companion star, or on the right here, where we have a black hole binary. So in the black hole star system, this is a little movie that kind of demonstrates it. Here we have a very bright blue companion star, and this is our black hole here. And you can see this accretion disk of matter I was talking about. And the black hole has so much gravity, it actually strips material off its companion star. This material falls into the black hole, and you then get these really powerful, very energetic jets, which we actually can observe in the X-ray. So these systems are normally called X-ray binaries because of this. And when we detect this incredibly powerful X-rays, we then can infer, well, we can follow it up with an optical telescope and see this big star and infer that there's a black hole binary system here. In terms of black hole binaries, I'm sure you've all heard of gravitational waves. This won the Nobel Prize in Physics in 2017, I want to say. So this is another way we can detect black holes. When we have two black holes that are orbiting each other, as they get closer and closer together, they actually cause ripples in space itself. And we can detect these as gravitational waves. And the way that we detect them is through either LIGO or Virgo, which has a laser, and essentially a gravitational wave would change the length. So we can bounce lasers off mirrors and measure this change in length and detect these gravitational waves. And it's really cool that just from the detection of gravitational waves, we can do a lot of physics, such as we know we can work out what the mass of the two black holes were. We can work out the mass of the final black hole, and some other cool things as well. And this plot probably needs to be updated. So this is from LIGO, and these are all the systems that LIGO and Virgo have detected. So all the ones in blue are these two binary black holes, and the scale here is stellar mass. So one stellar mass is the mass of the sun. And here, obviously, we have the neutron stars as well, and some of these funky systems where we weren't even sure if the final object that it produces is it a really large neutron star, or is it a small black hole? But anyway, I'm not going to go into too much detail because this is obviously a whole field on its own. But through the detection of gravitational waves, that's another way how we can observe, or at least detect, black holes in the universe. So another way that we can infer that black holes exist is through the effect they have on stars that orbit it. So this little movie here is zooming in to the Milky Way. So we're zooming in on the center of the Milky Way, and these are actual observations that you're seeing. So all the bright points are stars. And as we get closer and closer to the center of our galaxy, what we're going to see is the orbits of stars that have been observed over about 10 to 20 years, orbiting a central mass, which we now know to be a supermassive black hole. So as we zoom closer in, you can see that the quality of the images are getting slightly worse. And that's because it's actually really difficult to observe the center of our galaxy, because you just have so much dust, gas, and stars in the way. But when we get to the center, what you'll be looking at is a couple of these very central stars. So this one's a good one to look at here. And what you can see is that it has this quite eccentric orbit around seemingly nothing. And through these orbits, what we can do is we can do some physics to work out what is the mass enclosed in this orbit. And when we do that, we find that it's about 1 million times the mass of our sun in quite a small region. And the only known object that is that massive that you can't see in the optical is a supermassive black hole. And then finally, when I started giving these talks many years ago, I didn't include this slide, but I can now say that we can also directly detect black holes. So many of you will remember this. It was the first ever image of a black hole. And it was a supermassive black hole in the center of a nearby galaxy, M87, which is about, I say nearby, but it's still about 55 million light years away. And from this image, we can work out, again, lots of cool physics, including what's the mass of this supermassive black hole. And we find that this one is 6.5 billion times the mass of our sun. So what you're actually seeing in this image is the shadow of the black hole in the center. And then this bright ring is actually the accretion disk that we're observing. So how did they take this image? So it was through something called the Event Horizon Telescope. And this is a series of radio and submillimeter telescopes. And what's cool about radio telescopes is that you can actually link them all up together and essentially form a larger telescope. So from the Event Horizon Telescope uses observatories in Antarctica, Hawaii, Chile, North America, Europe, and they link them all up together and essentially make a telescope that is the size of the Earth. And the resolution of this telescope is so good, if you had a credit card on the moon, you could use this telescope to read the numbers. So it took them, how they took this image was over 4 nights from all these different observatories. And then they used a supercomputer and some fancy code to essentially stitch all these images together. But it was, it took them many years, and it was a huge team of astronomers all around the world. And in my opinion, this image is probably one of the scientific breakthroughs of the last, I don't know, we'll say 10, 20 years. And it was a little bit sad that, at least on my social media, when this got released, most people didn't really understand and were like, it's just a blurry image. But it took a lot of expertise, a lot of time to produce this image. And they're not done, they're not finished yet. They've got 2 more supermassive black holes that they're imaging. One of them is Sagittarius A star, which is the supermassive black hole at the center of our Milky Way. And I believe that one is going to be released this year. So keep an eye out. There should be another really cool image coming soon. And just a final note, some people asked, why didn't they start with the supermassive black hole in the center of our galaxy? Surely, because that is, you know, not 55 million light years away, that would be easier to image. But it's actually not, it's more difficult to image it because of all the stuff and stars in the way. But yeah, so that, with the Event Horizon Telescope, we can actually take images of black holes, which is really cool. Okay, so moving up in size and moving on to what I actually researched is something called active galactic nuclei, or AGN. And what an AGN is a supermassive black hole at the center of a galaxy surrounded by material or this accretion disk that's so bright it outshines the entire galaxy. And then we say that a galaxy is an active galaxy if it contains an AGN. So we've just been talking about Sagittarius A star, which is the supermassive black hole at the center of our Milky Way. So is the Milky Way an active galaxy? The answer is no. And that's just simply because there's not enough material at the center of our galaxy that's feeding the black hole and making it powerful enough to be an AGN. So AGN are just very powerful, very bright galaxies. And this is kind of the classical textbook model of an AGN. So you have your supermassive black hole, your accretion disk, and then further out you have essentially a donor of dust, which we call the dusty torus. And then you sometimes get these powerful jets, but you don't have to. And what happened was when we started looking at AGN, we started finding lots of different flavors of AGN. And it actually became what was known as the AGN zoo, because there were just so many different types. And in 1995, these 2 people came along and they suggested the unified model of AGN. And what that says is that all these different weird types of AGN are intrinsically the same object. They all look like this. But what's happening is we're just viewing them through different angles. And the main takeaway from this this image here is that when we talk about quasars, we're talking about an unobscured view to this accretion disk, so a line of sight that looks a bit like this. So this video should describe this unified model a little bit better. So here we're zooming in on an active galaxy, which is really bright in the center. And then we're going to go right into the central nucleus region. So here is this big donut of dust. And what this video is showing you is that as your line of sight moves, you're seeing something very different. So right now, if our telescope was looking in this line of sight, we're looking through this dusty torus. So we're looking at all this dust, and it's blocking a lot of the light of the accretion disk. And then as we move above this dusty torus and looking down onto the accretion disk, we're seeing this very bright disk of matter. And then again, if your line of sight kept moving up and you looked directly down the line of sight of the jet, it's going to look very different in our observations. So that's basically what this model is saying, is all AGN are the same. We're just looking at them in different through different viewing angles. So what's a quasar? Simply, a quasar is just the most powerful type of AGN. And the most powerful quasars that we've observed have luminosities that are about 1,000 times greater than the luminosity of the Milky Way. So you take 1,000 of our galaxy, you put them all together, and that's how bright some of these quasars are. So quasars are one of the brightest objects in the universe. And they're called quasar because the word quasar stands for quasi-stellar radio source. And I'll sometimes refer to them as QSOs as well, which is quasi-stellar object. And the reason they're called quasi-stellar radio sources is that they were first discovered in the 1960s, and they were discovered as these incredibly bright star-like objects that were very bright in the radio. And astronomers didn't really know what they were, so they gave them this name. We now know that they're actually a type of AGN, and yet they can be bright in the radio, but they're actually bright in a lot of different wavelengths. But like a lot of things in astronomy, the name stuck. So why do we study quasars in astronomy? One of the big reasons is cosmology. So because quasars are one of the brightest objects in the universe, we can see them at really great distances. And in astronomy, the further away you're seeing an object, the further back in time you're viewing it, because light takes time to travel. So the light from very distant objects has been traveling for a very long time. So essentially, you can use quasars as lampposts looking back in time to try and piece together how you got from the Big Bang to the universe we see today. And the most distant quasar that we've discovered so far is this one here, and I will probably have to update this very soon. So this one, J0313-1806, was discovered, I believe, January last year, because it was on my birthday. And this quasar is at a redshift of about 7.5. But most people don't work in redshifts. It's a funny unit that only astronomers seem to work in. So a redshift of 7.5 is about 13.6 billion light years away, which if you convert light years to kilometers, that's 1.3 times 10 to the 23 kilometers, or this number here, which I did work out how to say at one point, and I can't remember exactly how, but there is a word that describes this number. And then I just did a little bit of maths, and I thought, how long would it actually take us to get to this object? So if we jump in the fastest spacecraft we have, which is the NASA Solar Parker probe, this goes at about 150 kilometers per second. So if we went directly to this quasar, it would take this many years to travel to it. So they're incredibly distant objects, and 13.6 billion light years away corresponds to about 600 million years after the Big Bang. So this quasar formed very early on in the lifetime of the universe. And this is actually, this quasar posed a lot of problems for supermassive black hole growth models. And this is actually the abstract taken from the scientific paper that was released about this quasar. And I've highlighted this line here where it says that the existence of such a massive, supermassive black hole, just roughly 670 million years after the Big Bang, significantly challenges theoretical models of supermassive black hole growth. So what they're saying in this paper is there's actually a theoretical limit of how fast you can grow a black hole. So a black hole grows when material falls into it, but it can't grow at an infinite speed. There's some kind of cutoff. So what they did is they postulated if this black hole has been growing at the maximum rate it can for the lifetime of the universe, and so 670 million years, how big would it grow? And they've worked out that it can't get as big as 1 billion solar masses, which is what they measured it as. So either our models are wrong, our physics is wrong, or there's something else weird going on. And there's some solutions to how you can grow a black hole this early on, this massive. I won't go into them too much, but just a couple of, for those that are interested. One of them is that you could have these black hole mergers. So we talked about gravitational waves, we know black holes merge. That's actually the fastest way you can make a bigger black hole. So people have postulated maybe there was just many more black hole mergers in the early universe, so it kind of grew a lot faster than we thought, or that this theoretical limit, which is an approximation, is just way too simplistic. And we already have found some black holes where we've measured what we call the accretion rate, so how fast matter is falling onto the black hole, and we found that it's slightly higher than this limit. So we know that this limit is not a hard cutoff, but maybe it's, especially in the early universe, is just too simplistic to describe this. But this is an open area of research. People don't really know. There's a lot of funky models that and simulations people are running, but we don't actually have an answer yet of how you can grow black holes this massive. So kind of onto the kind of niche subject that I study. So most quasars, I said that quasars have this unobscured view to the accretion disk. And this accretion disk is very bright, predominantly in the ultraviolet and the optical. And this means that quasars have very blue colors. And it's actually how some of the quasar surveys select quasars, is they look on the sky and they say, if there's a really bright object that's very blue and very star-like, it's probably a quasar. But what we found is there's actually a small subset that show much redder colors, and these are what we call red quasars. And we think that quasars are red due to dust. So I've shown the background image is a nice sunset. Sunsets are red, and this is because the sun is low down in the sky. So the light from the sun travels through more of the atmosphere. This scatters the blue light, and so sunsets appear red. And we think a similar thing is happening in red quasars. There's some amount of dust that's scattering the blue light from the accretion disk. And just a little paper plug, a paper that should be published in the next couple of months, I actually show that this is the case, and I'll show some of these results a bit later. But just to show kind of that there's nothing, that this is quite a simple concept, these are two optical images I've taken from one of the telescopes that I use. On the left is a blue quasar, on the right is a red quasar. These aren't particularly pretty because they're very far away, so they just look like blobs on the sky. But the only difference between red and blue quasars is just their optical color. So red quasars look much redder. So why are red quasars interesting? Like, why do we care that some fraction of quasars look a bit more red? So the relationship between red and blue quasars has been debated over the last few years. So the two main scenarios that link red and blue quasars together are either orientation or evolution. So here is the orientation model, this is similar to that image I showed earlier with the that was explaining this unified model, but this one's just a little bit more involved. And yeah, for those that are really interested in all the weird different types of AGN, this is just showing the different lines of sight and the different objects that you get. And they all have these really confusing names, and people that don't work in AGN can never quite keep up with all the weird acronyms that AGN astronomers use. So in this model, we have our blue quasar, our normal quasar, and it's this unobscured view to this accretion disk, which we know is very blue. So the orientation model is very similar to the unified model of AGN, and suggests that a red quasar could just be looking through a bit of this dusty torus. And that's where we'd get the dust, and that's why they look red. So in this scenario, a red and a blue quasar are intrinsically the same object, which it's just due to line of sight. The evolutionary scenario, on the other hand, suggests that red quasars might be a special phase in the evolution of galaxies. And seeing this as a Durham video, you probably know where I'm going in terms of what we believe is happening. So the evolutionary scenario suggests maybe we start with two galaxies that collide. And you can imagine that that's a very energetic, messy process. So it produced this very dusty phase with a lot of star formation. And this is a starburst phase. And then there's so much material that falls into the supermassive black hole, it ignites a quasar. But there's still a lot of dust left over from this starburst phase. And this will be our red quasar phase. And then we think through powerful winds or jets or outflows, it blows away the dust and you're left with an unobscured blue quasar. And then potentially when there's just not enough material in the center, the quasar switches off and you're just left with a normal type galaxy. So what we've been doing at Durham is really trying to distinguish between these two scenarios. So how do we do that? How we need to actually select our red quasars. And to do this, we use an optical telescope. We use what's called the Sloan Digital Sky Survey, or SDSS. And the data release that I've used for a lot of my work was in 2018. And this has about 500,000 quasars that they've observed. So this is observed with optical data. And this plot here is showing G minus I, and these are two optical bands, and I is redder than G. So when you do G, subtract I, this gives you a color. And the higher the number, the redder the color. And then this is versus redshift or distance. And then what we do is we take quite a simple approach. Some might call it quite an arbitrary approach, actually. We select red quasars as the reddest 10% of this distribution. And we do this, we control for redshift, which is why this follows this shape here. So at every redshift, we just take the top 10% and we call these our red quasars. And then importantly, we also select a control sample, which I might refer to as the blue quasars or control quasars. And we do this as the middle 50% of this distribution. And why this is really important, and actually there's other teams looking at red quasars and they don't always take this step. It's really important because any results you find for the red quasars, we can then compare to the control quasars or the normal population of quasars and say, are these properties different in the red quasars? And some groups don't do that, and it means that they publish a paper saying, oh, look at these really cool, interesting properties we find for our red quasars, but they don't actually compare to anything. So the blue quasars could have also interesting, cool properties. So it's always important to have a control sample. So what do we find for red quasars? First of all, and I've already kind of hinted at this, we find that the red colors is due to dust. So I've said that it was likely due to dust, but there's other things that could cause the colors to be red. Examples of that is if the quasars are have strong radio emission. This can make the light look redder. Host galaxies are very red. So if there's strong contamination from the host galaxy, this can actually mask the blue light of the quasar and it make it look a lot redder. Or they could just be intrinsically red. For some reason, their accretion disk just looks redder than usual. So to distinguish between these different scenarios, I use spectroscopy, and I'll just pause this a sec. So what spectroscopy is light on the y-axis compared to wavelengths. So this is UV, optical, near infrared. And the solid blue line is a spectrum of a blue quasar, and then the red lines are spectra that I have of red quasars. So what you can see for the blue quasar is it has this underlying rising continuum, and this is a very blue continuum. And then these kind of bumps are what we call emission lines. These are caused by different kind of molecules. So here we have hydrogen. This line here is oxygen, magnesium, and then a couple of carbon lines. And through fitting these spectra, we can actually work out a lot of properties of the system. And what I did is I fitted what we call dust extinction curves, so dust models essentially. And I applied some dust to the blue quasar. I wanted to see what does the spectrum look like if I just add dust to a blue quasar. And that's what this gray line here is showing in this little movie. It's just this blue quasar plus some amount of dust. And as you can see, when as you increase the amount of dust, you create this spectral turnover that we see in our red quasars. So hopefully I do this a bit more quantitatively in the paper, but hopefully just by eye, you're convinced that just by adding dust to a blue quasar, we can recreate the shape of the red quasars very well. So this tells us that dust is the main cause of red colors in red quasars. The other part of my research has been focused on radio. And what we find is a very remarkable property of red quasars is that they have increased radio emission. So if you look with a radio telescope at a sample of red quasars and a sample of blue quasars, a higher fraction of the red quasars would be detected in radio. And this graph is a little bit busy, but essentially that's what it's showing. So this is the radio detection fraction versus radio flux or radio brightness. And then these are just different samples I've used, but the red line is the red quasars, the blue line is the blue quasars. And hopefully what you can see is the red line is always above the blue line. And this is probably better shown in this bottom panel here, which is the radio detection fraction of the red divided by the radio detection fraction of the control. And you can see it's always above 1. So what this is saying is that red quasars have enhanced radio emission compared to blue quasars. And why this is really exciting is you cannot explain this with the unified model of AGN, with this orientation model. And that's because radio emission is not affected by dust. If it was, then you wouldn't be able to get a radio signal in your house because it'd be blocked by the walls. And if anything, if you were to imagine that a blue quasar is this more face-on object, the jet is normally what is causing this radio emission. And if you're looking more directly along the line of sight of the jet, you might expect the blue quasars to have enhanced radio emission. But we find the opposite, and we can't explain this with this unified model. So this rules out this orientation model alone, and it suggests that there's some more fundamental differences, something more fundamentally different about red quasars rather than them just being inclined blue quasars. We then look at, still in the radio, we look at radio morphologies, and this simply just means the shape of the radio emission when you take a radio image. And what we do is we look through all the images and we categorize them into these 4 different groups. So either they're faint, where we just can't really, they're too faint for us to tell what the shape is. compact, when it's just a circle, essentially, it means that it's unresolved at the resolution of the radio survey. Extended, where you definitely see like a little bit of extension, and then what we call FR2. And that's just a classification, which means we can see two clear lobes, which are caused by a big radio jet. And in some previous work by our group, they did this analysis using this radio survey called the Faint Images of the Radio Sky at 20 centimeters, or FIRST. And in my work, what I did is I used some higher resolution, deeper radio surveys. So this is the data that I was using, and these are the exact same objects as the one above them, but with this higher resolution radio data. So it's essentially like if you need glasses, putting on your glasses for these ones down here. And what you can see is that, for example, with this compact one where we couldn't really see anything, with this high resolution data, we can now clearly see there's a bit of a tail on this quasar here. And then my favorite one is this one here, where we definitely see there is some kind of structure to the top one, but in the bottom one, we're actually resolving out these two lobes of a jet. And then what I did is I went through the images of all the red and the blue quasars, put them into these categories, and then looked at what fraction are in these different groups. And again, if the orientation model were correct, then we wouldn't expect there to be a preference or any difference between the red and blue quasars in terms of how their radio emission looks like. But we find that red quasars have a preference for small scale radio emission. So they have enhanced radio emission, but it tends to be on small scales. They're not these massive, really spectacular radio jets that you might have seen images of. And this actually does support this evolutionary scenario, because if red quasars are younger, then maybe this is a small jet that just hasn't had the time to grow into a really large jet because they're in this younger phase. But yeah, so these results, they support the evolutionary scenario. And what we think might be happening is that dusty winds might be present in red quasars. So we think that either a jet or a wind is hitting some dust in this red quasars. This causes shocks, and these shocks causes radio emission. But I mean, that's probably getting a bit too technical. This little movie basically shows an idea of what a dusty outflow would look like. So here you have this dusty torus, but above and below in these polar regions, we have this dusty outflow. And in work that with our collaborator, Gabby Calistro-Rivera, she actually found that red quasars do show evidence for these dusty outflows. But yeah. So that was kind of a summary of what the work I've been doing. I just want to briefly just talk about a couple of exciting projects we've got upcoming. So first of all, I'm really involved with what's called the Dark Energy Spectroscopic Instrument, or DESI. And DESI is just, DESI is an instrument that does spectroscopy, like I showed you with that dust extinction movie. And it's on this telescope here. This is the Mayall telescope in Kitt Peak, Arizona. So DESI is predominantly an American collaboration, but it's international, and Durham's one of the partners. It actually helped build a bit of the instrument. And DESI's just started a 5-year survey to observe all of the northern sky. And it started May last year, so it's very early on, and its plan is to observe 30 million galaxies and, what I'm interested in, 3 million quasars over the next 5 years of the survey. And within this collaboration, I have a program to look at red quasars using this instrument. So yeah, just to look at one of these red quasars that have already been observed. This is quite a cool website, actually. Anyone can have a look at this. I put the link up here. And essentially, this just gives you a map of the sky, and it's all the imaging that this instrument uses to select what it wants to observe. And if we just zoom in to a little patch of the sky, here we see a beautiful spiral galaxy, but I don't really care about them. What I care about is this little orange dot here, which is actually one of the red quasars from my program that DESI's already observed. And what we find is that the program's working. We are finding a lot of red quasars. And what's really cool about DESI, why it's better than SDSS, which is what our previous work was based on, is it's finding much more redder and fainter objects than SDSS could. So we're really excited about this program. And so far we have about 500 red quasar candidates, but we're hoping maybe to get about 10,000 over the next few years. So yeah, this is something I'm quite excited about. And then finally, we have more radio data. We have it from what's called the Giant Meter Radio Telescope, or GMRT. And this is a telescope in India. And the reason we got this radio data is that it's multi-frequency. So we have radio data in 4 different radio bands, and we can use that to hopefully try and distinguish between whether the radio emission is produced by winds or by jets. So you probably noticed that during my talk, I kind of use winds and jets interchangeably, but that's kind of because we don't really know. We think that it's probably winds, but we can't rule out jets. But using this radio data, we might actually be able to determine if it's definitely winds or definitely jets. So I was actually quite lucky that I went out to Kodad in India to take the observations. And why I say I was really lucky, this was February 2020. So I was cutting it a little bit fine, but I'm glad that I got in an observing trip before, yeah, everything went a bit, yeah. Let's just say I haven't done a lot of traveling in the last couple of years, which is a shame because that's one of the benefits of doing astronomy is you get to normally go to lots of cool places. But yeah, just a little summary of my trip. These are the food I ate, and I had curry 3 times a day for 10 days. And I'll be honest, I did not get tired of it. It was amazing, and I would happily have curry all the time. And yeah, so here's me by a couple of the 2 antennas. So I mentioned earlier that with radio astronomy, what you do is you link up different telescopes. So you link up antennae. And here are 2 of they're 30 meters in diameter. And you can just get to wander around the site. It's really cool. And because with radio astronomy, you can actually do it in the day. You can watch these massive telescopes actually move during the day. Here's another picture of me. This is in the control room of the telescope, and I'm here pretending to do some work, but it's really these guys here that are the telescope operators that do do the complicated side of the observations. And then finally, here's just a lovely sunset photo. And I guess a kind of funny story about this is that we spent quite a lot of time in the evenings going and taking these really cool sunset photos. And then someone said to us, they were like, oh, you're not going out, you know, in the evening, are you? And they were like, you know, that's when the leopards come out. And I thought that they were just winding us up because we were, you know, clearly foreigners. And then I Googled it, and they are correct. Apparently there's a booming leopard population in Kodad at the moment. And they tend to come out at dusk and dawn. And it's advised that you don't wander around the site, because they have had leopard sightings before. But luckily we didn't see any leopards, and it was all good. But yeah, that's the end of my talk. Thank you very much, and I'm happy to take any questions.
Vicky, thank you for a fascinating talk. Can you stop sharing your screen, please?
Yeah.
We're looking for questions. And electronic hands, please. Wave at me. I've got a couple of screens, so I'll be a little bit slow on the uptake. Andy Devey, can you unmute yourself, sir?
Hi, Vicky. Excuse me a second. Really enjoyed your talk.
Thank you.
Also, obvious passion behind it, so I can see what's driving you, and I think you're going to make quite a number of discoveries. When you mentioned about the size of the black hole that was sort of only 650 million years after the Big Bang, and you mentioned about the rate of accretion. Do you think there's a possibility that huge black holes could be a remnant of the Big Bang itself?
Oh, that's a very interesting question. I guess the short answer is I don't know. The theories that I've read about, I don't think that's one of them. It's more likely there's something that's quite interesting is they're looking for, I don't know if people have heard, population 3 stars. And these are just these theoretical supermassive stars that were formed very shortly after the Big Bang. And they would have been so massive and so bright that they wouldn't have lasted very long. And those could potentially have made just very massive black holes to start with. Another idea is that you have what's called direct collapse black holes. So instead of getting a dust cloud, collapsing that down to form a star, then collapsing the star down to form a black hole, maybe early on in the universe, these dust clouds were just so dense and has so much gravity, they collapsed and formed a black hole, but like skipped the whole star stage, just went straight to a black hole. And that's theorized, if that had happened, you would have again made a more massive black hole to start with. And if you start with a more massive black hole, then obviously you don't need to grow it for as long to get it to that massive. So yeah, there's some weird theories, but we really don't know at the moment what the answer is.
The other thing, in the early days, things were much closer together, so the potential for collisions would have been much higher as well.
Yeah, exactly.
Thank you.
Okay, Andy. A question from Claire Booth. She says, thank you for a brilliant talk. Can you tell us what our nearest AGN and quasar are to Earth, and how far away are they?
That's a very good question. So I would always talk about AGN and quasars as these really distant objects, but you can get them quite close by. So I'm trying to think. I work in redshift, which is really not useful. So in my work, I do a cut of about a redshift of 0.2. Don't know if I can look up. But there's a few really famous AGN, and because there's ones that are very close by, and they're so close by that you can do really good quality imaging. So much better than any of the stuff that I've done, because everything I've done is too far away. So you just get these blobs. Yeah, I don't know the exact number because I work in redshift, but I guess.
Vicky, give us the redshift numbers and we can look it up afterwards.
So I think the closest one, you can get them down to like a redshift of like 0.05.
Right, I'll ask one of our elves to get onto that.
But yeah, it's
so
because you have these different types of AGN, the ones that are really close by to us tend to be the lower luminosity. They don't tend to be the quasars. Quasars are more prominent in the distant universe. But
okay.
Yeah.
I hope somebody's beavering away at the moment now, looking that up. Ian Hargreaves.
Yes, thanks very much, Paul, and thank you, Vicky, for an excellent talk there. I really enjoyed it. You were saying that the differences between red and blue quasars might be this dust that you were talking about, but could it not be that the quasars are more massive, the whiter ones, or the bluer ones rather, are more massive, and therefore the accretion disk is orbiting a lot faster and therefore generating higher temperatures, and hence the bluer light.
Yes, that's a good point, and I didn't actually have the time to go into it, but another thing you can do with spectroscopy is you can fit what we call accretion disk models, and from that it tells you like the accretion rate, the size of the black hole, the spin of the black hole, things like that. And you're right that we looked at that because that could be one thing that would be explaining the differences. If you have differences in the central engine, like the size of the black hole, the rate of accretion, this could be driving the differences we see in the radio as well, between red and blue. But the short answer is we don't find any differences, any significant differences in the accretion disk models between red and blue. I do have a plan there's someone in the department who's like a world expert on accretion disk models, and she has like a lot of more complicated models than the ones that I've tried. So we were thinking of maybe a future project is to do this in a more detailed way. But to first order, they have similar size black holes, similar accretion disks. The only difference, the main difference we see is this presence of dust, which, to be honest, it makes them even more, in my opinion, even more interesting, because why does just a little bit of dust, and we're talking about the amount of obscuration is about a piece of paper's worth. So it's a really small amount of dust, yet this then causes these really different radio properties we see. So yeah, it's something we're still trying to work out. We have some idea of what a red quasar could be, but we're still not completely sure. We're doing some more tests, but yeah, we don't find any differences in the accretion disks.
Thank you. Thank you.
Okay, our elves are reporting back to us as I speak. Doug Edworthy tells us that a redshift of 0.02 is approximately 275 million light years. Roy Gunson backs that up with a redshift of 0.05 is approximately 688 million light years. And Trevor Worrell, all the way from Spain, tells us that the nearest AGN is Centaurus A, which is 11 million light years. So I think that just about sums that question up. Robin Catchlove.
Hello, yes, thank you very much for a brilliant talk. I'm going to expose myself as being a bit thick here, I think, but what I'm intrigued is the images that you show of black holes have the accretion disk, but then the jets. Now, my thinking is that if you've got a black hole, it shouldn't have a jet coming out of the top of it. And I wondered what caused that, please.
That is not a stupid question. That's still an open research area at the moment. Is jet physics is really poorly understood. So when you have, I think the idea is if you have this spinning black hole, you have a jet that's launched very close to the black hole, because obviously, yeah, nothing can be launched out of black hole because of black hole. We think that there's some region very close to the top and the bottom of the black hole that's producing this jet, and it's something to do with magnetic fields. But there's a joke in astronomy, is I think people here might know, is that when we don't understand something, we just go, oh, it's something to do with magnetic fields, because magnetic fields aren't particularly well understood. And we have simulations of AGN that if you put a spinning black hole accretion disk and then you press play, you form these jets. So we know that you can form a jet, we just don't know exactly how, where the region is, how close the black hole it is, or exactly how this jet is launched, apart from that it's something to do with magnetic fields. So I don't actually know the answer to that.
Oh, that's great. Anyway, you've given me, I thought it might be to do with spinning, but that just adding magnets as well helps. Thank you very much.
Yeah.
Okay, from Rodney Buckland, what can the square kilometre array do for AGN research?
Oh, it's a good question. And there's someone, part of our group is Dr. Leah Morabito, and she was actually on BBC News, I think, talking about SKA. So she's really involved. I haven't, I'm not involved, but it's going to be really good, mainly because the radio surveys I've been talking about are all Northern Hemisphere. So like first is Northern Hemisphere. We don't have a great deal of radio data in the Southern Hemisphere. So that's kind of one thing that this, I think would be really interesting, because then we'll get all sky coverage. And it's also it's going to be very deep. And the deeper you get, the kind of fainter radio emission you can detect, because obviously all the telescopes have a cutoff. There's a limit to how much radio flux you can detect. So with the former PhD student in our group, she used FIRST, and this is quite shallow. So she was only really picking up the really radio bright things. And then in my study, I used some deeper data, but a lot of the deeper radio data is on these very small regions. So I did this really, really cool paper, but my source statistics were really low. So I had huge error bars on a lot of things because these regions of the sky were just very small. So I didn't have many red quasars. Whereas the SKA is going to be large sky, but it also deeper radio data. So I think, it's going to be, pretty revolutionary in terms of radio data. But yeah, I currently don't have too many plans to use it. But yeah, there's definitely a lot of things that could come out from a lot of astronomers, including people at Durham.
Okay, Leah Morabito talked to us back in November.
Oh, did she? Okay. Was she talk? So she's also involved with LOFAR, the low frequency radio telescope.
The title of her talk was Supermassive Black Holes, How Do They Impact Galaxy Growth? And for those people who missed the talk, it is posted on our YouTube site, which is available via the gallery on our website. So if you want to catch up with it, there it is, it's sitting there. Peter Lloyd.
Well, thank you, Vicky. Very interesting talk. I was particularly interested in your proof that the reddening of the quasar is due to scattering by dust or whatever. Is that assuming the scattering is Rayleigh scattering?
Yes, I believe so. I think there's, the scattering process is a bit more complicated, but I think it is Rayleigh scattering just multiple times, if that makes sense. Yeah, short answer is yes. Yeah.
Thank you. Hence, yes. Now I understand it. Thank you.
Okay, Peter. Steve Taylor. You need to unmute yourself, Steve.
There we are. Much better. Vicky, all I wanted to ask you, you showed us a picture of a red and a blue quasar, which you said you'd observed through whichever telescope. What instrument were you using for those views?
So that was SDSS. I think, again, all of this data is publicly available. So you can go on the SDSS website and you can download images and spectra. You just put, especially SDSS, it's got a really cool website called SDSS Explorer, and you just put in an RA in a deck. And then it gives you the spectrum and the image. So I just for an example, just chose a couple of the brighter red and blue quasars, put it into this website, and then just saved the images. Yeah, those were from SDSS.
Oh, we're all a bit disappointed.
Thank you very much.
We're all a bit disappointed that you didn't actually take those images yourself. But
yeah.
Okay. I'm looking around for any other questions. I'm not seeing any yellow hands. I'm just going to do a quick scan to make sure that nobody's waving at me. Oh, Ian Hargreaves doing both.
Yes, thank you again, Paul. And once again, thank you very much, Vicky. Question I've got is, when you're looking at these very, very, very distant quasars that are no more than a couple of pixels or so on an image, how do you determine the mass of those quasars?
So just to note, so in my work, I don't look at the really high redshift quasars, and that's basically
right.
because obviously with color you have redshift effects. It's why we control for redshift. But if you get beyond a certain redshift, so my cut is at 2.5, anything beyond a redshift of 2.5, you can't trust the colors. It could just be red due to redshift. But in terms of getting the mass, if you had a really with this high redshift studies, they kind of determine some candidates and then they follow it up with deeper observations. And if you get a spectrum, you know, I showed the spectroscopy with the different emission lines. You can measure the flux of those emission lines, and those are like a proxy for black hole mass. So it is a bit of an approximation, but you can get black hole mass if you have a spectrum and you can actually detect some emission lines. Then you use these like scaling relations between the width and the flux of these emission lines, and that gives you a black hole mass. And that's how I think the majority of black hole masses are measured in these objects. But yeah, you need to have a good enough spectrum that you can actually fit a model to these emission lines.
Okay, thank you very much.
Okay, ladies and gentlemen, I think we've worked Vicky hard enough for this evening. Can I ask everybody to give Vicky a big Mexborough and Swinton Astronomical Society thank you for a wonderful talk. Thank you, Vicky.
Thank you very much.